Yeah, so I would like to just take questions if there are questions. Otherwise, yeah. So I thought we could have this meeting and this could help in kind of answering any questions that you may have for the exam or for some other understanding some other thing. So the exam is next week, and so basically initially we saw deterministic finite automata, then which is equivalent to regular languages. So DFAs, NFAs, and then regular expressions. Then we saw uh, context-free grammars. We saw that it is equivalent to pushdown automata and context-free languages. And then we saw different properties of this. In both regular languages and context-free languages, we saw how to prove that a language is context-free or regular, and also how to prove that something is not context-free. There is also this pumping lemma for regular languages as well as context-free languages. Then we saw what are the limits of computation. We understood the computation model of Turing machine. We talked about what are the things that you can compute, and then surprisingly there were languages that you cannot decide on, right? There are undecidable languages. So even with infinite computation or power or time, still you cannot answer. So there are questions that you cannot answer in an algorithmic manner, right? And so we saw decidability and undecidability. Then we finally saw some parts of complexity theory, where like what one of the most important resources was time. So what can be efficiently computable? So in terms of time, we say something is efficiently computable if it can be computed in polynomial time. So polynomial time is the class of languages that typically is considered to be efficiently computable. So it's denoted by the letter P. Then we saw non-deterministic polynomial time, which is NP. We saw NP completeness. We saw Cook-Levin theorem. We saw reductions. We also saw reductions while we were doing undecidability and decidability. But here in polynomial time, NP completeness, we had restricted reductions, meaning the reductions should be computed in polynomial time. And finally, we saw some aspects of space complexity there, which is another important resource in terms of computation. So this is the rough summary of what we saw throughout the semester. If there are any specific questions, I'll be happy to answer. Otherwise, otherwise we can close the session. If you have questions, please feel free to unmute yourself and ask. From Vishal, will the exam be in the assignments objective-like format? Yes, the answer is yes. It will be objective-like format. Also, is Turing machine our best option for computation? Have we moved beyond it or not? This is kind of a fundamental model of computation. So it will be like, of course, modern computers don't look like Turing machines, but you could say that underneath all the frills and processing speeds and optimizations, you can view it as a Turing machine, right? The model, there is some memory, there is some where you write or read, and there is some processor that decides based on the memory and based on some states, it decides what to do. So that's kind of a very standard model. There are some things like quantum computation, which where certain operations happen differently. But still, I think this is a very basic model, right? Quantum computation is a different setting altogether. But we are not seeing that in this course. If you're interested in that, you perhaps have to take a course, separate course. I'm not sure. I don't know if there may be a course on NPTEL for quantum computation. But the optimization happens in real world computers, like the computers that we have now are not what we had like 10 years back. And what we had 10 years back were much better than what we had 20 years back, right? So things are evolving in terms of the availability of memory, in terms of speed, in terms of, like, say, multi cores or parallelism. In different ways, there are improvements. So even though it is all based on Turing machines, you could say that it's classical computation is still based on Turing machines. Yeah, but the improvements are happening in some other way. No, it's the difference between the question is, my guess is, do we have the option of moving beyond left or right? So uh, the distinction in the quantum computation happens in the way bits are stored. And basically it's the here we have symbols which are written and which are fixed symbols. It may be binary, it may be decimal, it may be something else in the classical computation. In quantum computation, we have this notion of superposition. So the same time, like you may have some vectors of bits, and which could be a certain value, which could be one with a certain probability and zero with some other probability. And you won't know what you have in there until you do what is called a measurement. And so once you measure you get to know what is there. And then there is also this concept of entanglement, meaning there could be two memory locations where which are related in a certain way. So if you measure one of them, the other one also gets decided based on whatever relation they have. So that this is the kind of, at a very, very high level, this is what makes quantum computation different from classical computation. Going beyond left or right is not really adding much. Like if you have, let's say, a Turing machine, if the Turing machine tape can move in a plane, let's say, instead of a one-dimensional tape which is long, and if you have an entire plane to move around, let's say a two-dimensional grid, it'll still have the same similar powers as a classical, as a standard Turing machine that we define. Any other questions? Can you please explain one's PDA? So I so pushdown automaton is something like a regular, I say, like a deterministic finite automaton, but it has an additional stack along with it, right? So that is the main difference. There is a limit to how much time I can spend in this session. I can explain, but I'm just trying to find out the notes. Let me just share the screen. Are you able to see the screen? Are you able to see the screen? So basically, pushdown automaton, there is this there is an input tape. It is like a deterministic finite automaton, but in addition, you have a stack. So based on what is there in the stack, So you get to read the input as well as what is there in the stack. And based on what is there in the stack and what is the input, you will make the move. You will move ahead, or you will push the stack, you will pop the stack, and you keep operating. And finally, at the end, and the accept reject conditions are similar. At the end, you should have a way to read the entire input and reach an accepting state. So this is, in a very brief way, this is what pushdown automaton is. Which topics should be prepared for the exam? And one more point about pushdown automaton is that it's the way we defined it. It is not deterministic, and there is a deterministic pushdown automaton which I do not get into during the course, but it's not like if you're curious, you can read up about it. I think there is this SIPSR has a section on deterministic pushdown automaton. Unlike finite automaton, where deterministic and non-deterministic finite automaton have the same power, and what we saw was not deterministic pushdown automaton. Deterministic pushdown automaton are actually less powerful, meaning the class of languages they can decide are a proper subset of what non-deterministic pushdown automaton can decide. So whatever we said pushdown automaton was actually not deterministic, because the moves that they made were non-deterministic. Okay, now coming, which topics should be prepared for the exam? So the exam is for the entire course, right? So you should know most of the topics. Like there's no specific thing that I want to suggest. But if you have understood, if you have followed the course well and you have understood most of the topics, you should be good. Exam pattern, I think I already answered. It'll be like questions that we saw in the assignment. Yeah. Yeah, the exam I have set 400 marks. Yes, that's correct. But it's all questions like what you saw in this, or questions of a similar type. Yeah. Please ask questions. Do you have questions? That's it. No one else has any other questions. NP and P explain, please. DFA of L contains ABA as a substring. What exactly is the question? You're asking how to construct a DFA that decides this language? Okay. So first let me answer that question. So unfortunately, I'm on a laptop where I cannot draw. But the idea is, I think there has to be a state. I'm assuming that the alphabet is A and B, just two symbols. So we should be able to go to, there should be a start state, and there should be a start state, and if you see an A, you should move to another state. And if you see another A, you can remain in that state, because so the idea is you want to remember how much of the substring ABA have you seen. So if you see an A, you move to the second state. Let's say second state. And if you see yet another A, you remain there because still you are seeing an A. And if you see a B from the second state, you move to the third state. So now the third state indicates that the last two symbols that you've seen is A and B, right? So A and then B. And then if you see another B from there, now you have to go back to the start state because ABB is not going to help us, right? If you see another A from there, you go to an accept state. Is it clear what I'm saying? And once you are at the accept state, you can just loop at the accept state. So I think 4 states should be good enough, is what I feel. So the start state, there is an arrow for A to the second state. And in the second state, will loop if it sees an A. From the second state, if you see a B, you will go to the third state. And from the third state, if you see an A, you go to the accept state. From the third state, if you see an from the third state, if you see a B, you go back to the start state. If you see an A, you go to the accept state. And whatever you see at the accept state, you loop because accept state means you have already seen A, B, A. So very at a very high level, you are trying to, the start state is just started. And the second state is like you have seen an A as the last symbol. That's what you're trying to remember. Third state is the last two symbols were A and B respectively, right? The fourth state is you have seen A, B, A. You have just seen or you have seen at some point. It's an accept state. Start state means whatever the last symbol you have seen is not good enough to build on and make A, B, A. I get confused in the concept that which state I have to go back. I think the way to do it is you just you prepare a DFA, you write a DFA, and then go through it, you study, you try, play with it and see which string goes to which state. And you try with various strings, try with strings that have ABA in it, that do not have ABA in it, and see how the strings progress. And now let me try to address the next question. NP and P explain. Okay, so I'll try to find, maybe it's week 9, is it? So NP is a class of languages that have a non-deterministic time non-deterministic polynomial time decider, meaning it can decide a language in non-deterministic polynomial time. Another way to view an NP machine is it has a polynomial time verifier. So if I tell you a graph is 3-colorable, we do not know of a way to decide if the graph is 3-colorable in polynomial time. But if I give you a coloring and say that this is a valid 3-coloring, you can verify that this is a valid 3-coloring. You can just go through the vertices and see whether it's a valid 3-coloring. So, which means the problem of 3-colorability is an NP. In polynomial time, you can, if I give you a certificate saying that this graph is 3-colorable, you can verify it. So NP in a sense is the class of languages that have polynomial time verifiers. P is the class of languages that have polynomial time deciders. So verifying seems to be an easier thing, right? If I am giving you something to verify, it should be easier than deciding something. So verifying in polynomial time should be easier. So anything that you can decide in polynomial time, you can also verify in polynomial time. Hence, P is a subset of NP. However, it is not known whether you actually get more power by going from deciding to verifying in polynomial time. So we do not know if NP actually is more powerful. So the big open question in computer science is to decide, is P equal to NP or is P a proper subset of NP? Right. So this is the distinction between P and NP. So this particular notes is very interesting. Like it's asking the same question, but in a different way. Or it's not asking the same question, but it's asking, is everything polynomial time computable? Okay, this does not have NP here. Non-deterministic polynomial time. So anything that you can do in deterministic polynomial time, you can also do it in non-deterministic polynomial time. Like three colorable, like for instance, two colorable is in deterministic polynomial time, but you can also do it in non-deterministic polynomial time. But three colorable is also in non-deterministic polynomial time. The question is, can you do it in deterministic polynomial time? So we don't know if P is equal to NP or is P a proper subset, meaning P, there are things in NP that are not there in P. Are there problems that are in NP, which mean they can be verified in polynomial time, but cannot be decided in polynomial time. That's the, so in very, very simple terms, this is P versus NP. Vishal's question, I have managed to complete only up to Turing machines. What's a good strategy to cover the entire syllabus in the given time? Uh, right. I think one thing is, first make sure that whatever you learn well. I don't really have any suggestions for this. And also try to learn what the other things that you have not learned. You basically have to like 4 or 5 days to the time and study. In mapping reducibility, every question is a new approach. I think which you have covered, I understood, but when a new question comes, I think if you ask a question, it will be mostly, I think I'll be reasonable in the expectation. It will be mostly things that you are familiar with or things that you are similar to what you're familiar with. But how do you approach a new question? Maybe look for patterns. If you see a problem, is it similar to, like, if you see a new question, think, is this problem, let's say a problem X is is NP complete or it's undecidable. Now, is it similar to another undecidable problem? Just and or NP if you want to show a problem, P is NP complete. Now, is P similar to the known NP complete problems? For instance, is P similar to subset sum? Is P similar to clique? Is P similar to vertex cover? Is P similar to set cover? Right. So you have some questions that you know are NP complete. You try to think about these things. And in any case, it's a, yeah, we are not asking derivations because in this mode, it's difficult for me to ask like subjective questions where you write answers and I get to correct that. But in general, the answer to your question is that it comes with experience. If you do more and more problems, you start getting familiar. Any other questions? No other questions? There are no other questions. Maybe we could close the session. Thanks for coming to this live session. Thanks for attending the classes or listening to the videos. And thanks for the questions. Yeah, hope you are able to prepare well for the exam and answer well for the exam as well. I suppose there are no more questions. I hope the classes and the videos are helpful for you to learn. Okay. Is there somebody from NPTEL? They can help close the session. Is there somebody from NPTEL? Can you close the session? Okay, I think NPTEL may close it in due course. Thanks all for attending, and thanks for the questions. I think I'll log out now. Thank you all. Bye bye.